Hello and Happy New Year. This is the second course in the Algebra series of UCSD. In this course, we will learn about ring theory, and at the end of the course, we will learn a bit about field theory. Even though this is the second course, let me start with a historical note, pseudo-historical note, on what algebra is about and why it had been developed. So historically, a large part of algebra had been about zeros of binomials. In fact, the word algebra comes from the name of a book written by Al-Khwarizmi, a Persian mathematician, where he gave algorithms on how to find zeros of degree 1 and degree 2 equations. I should say that Khwarizmi was a Persian mathematician. I'm Persian. I should start with this historical note. So the degree 3 polynomials, or the cubic equations, had been developed or had been solved, almost solved by Khayyam, another Persian mathematician. He did not completely solve cubic equations. The solution of cubic equations had been completely done by Italian mathematicians, and it has actually a very nice history behind it. I encourage you to Google it and find it out and read about it. Del Ferro, an Italian mathematician, solved it, but so there is a dispute. Then the degree 4 equations had been solved by Ferrari and other Italian mathematicians during the 16th century. Degree 5 equations was not solved till later in the 19th century, and there is a good reason for it. In fact, in 1824, Abel showed that a generic degree 5 equation cannot be solved using radicals, addition, subtraction, multiplication, and division. It's quite surprising. And in 1832, Galois showed how one can use symmetries of this system of numbers that come out of zeros of a binomial to understand whether or not those zeros can be described using radicals, division, addition, multiplication, subtraction, and division. And hopefully by the end of the third course of this algebra series, we will get to Galois theorems. I should say that another source of motivation and influence in development of modern algebra had been Fermat's last conjecture. So Fermat conjectured, in fact, he claimed that he can show there are no positive integers, a, b, and c, such that a to the n plus b to the n equals to c to the n. So if you think about it, this problem has two new directions compared to zeros of single variable polynomials. So the first thing is that it's a multivariable polynomial. And the second thing is it's a Diophantine equation, meaning we are asking for the set of solutions not in real or complex numbers, but rather in set of integers. So these type of equations are called Diophantine equations, and both of these directions, both going from single variable equation to multivariable equations, and from real or complex to integer or rational, both of these directions had been influential in development of modern algebra. The first one can be considered to be the foundation of algebraic geometry, and the second one can be understood as the foundation of algebraic number theory. But I've mentioned the system of numbers in this pseudo-historical note and comment. Let's see what it is in a precise way, in a systematic way. So I'm going to share my notes with you, so that way you can see, you can follow better. Okay, so I have to use this. Okay, so in group theory, you learn that a non-empty set with a binary operation with certain properties, meaning the binary operation should be associative, it should have a neutral element, and every element should have an inverse. And then we called it a group. Now here, a non-empty set with two binary operations, one of them we call addition, the other one we call multiplication, is called a ring if it has the following properties. First of all, with addition, it should be an abelian group. So we need to have a neutral element. We need to have a neutral element. And for every element, we need to have an inverse, negative of that element. With multiplication, it should be associative. I mean, the multiplication should be associative. And the connection between addition and multiplication is the distribution property. And as you can see here, I'm emphasizing that the distribution property should be available. We should have distribution property from both sides, from left and right, because a priori we are not assuming that A times B is the same as B times A. In fact, if a ring has this extra property, then we call it a commutative ring. Now, we do not in general assume that our ring has an identity. If it does, then we call it a unital ring. And this element, we will show that it is unique. And when we show that it is unique, then we can call it the identity or the unity of this ring. In this course, I prefer to refer to this element as the identity instead of the unity, in order to avoid confusion with unit elements, as we will define them later on. I should say that in your book, every ring is assumed to be unital, but it's not so standard. So I prefer to use this notation, this naming of unital rings instead of referring to every ring as unit. Okay, so now we define what is a ring, we define what is a unital ring, and now we want to see what are the examples. So these are the basic examples of rings: ring of integers, ring of rational numbers, ring of real numbers, and ring of complex numbers. These are basic examples of rings. And let's see one non-example. If you think about set of non-negative integers, they are of course closed under addition. They are closed under multiplication. We do have a neutral element with plus. We do have identity, in fact, in this set. But this is not a ring because simply set of non-negative integers and plus do not form a group. In fact, besides 0, no other element has a negative inside this set. So it's not an abelian group, and therefore it's not a ring. Not every ring is unital. For instance, if you think about the set of even integers, it is a ring. It's closed under addition, and it's closed under multiplication, and every even integer, the negative of every even integer is also an even integer. 0 is an even integer, and so on. It is a ring, but it does not have identity. And not every unital ring is commutative. So maybe the source of many examples would be a set of matrices. You learn about matrices in linear algebra, So n by n matrices with entries inside real numbers or complex numbers, and they form a ring using addition and multiplication of matrices. In fact, we can construct matrices out of any other ring. We don't need to start with real or complex numbers. We can start with any ring A and then consider n by n matrices with entries inside this ring. And as you can see, when I'm defining multiplication and addition, I'm working with I only need to be able to multiply and add entries of these matrices. So as soon as I know that these entries are within a ring, I can define matrix multiplication and matrix addition. So, and it's actually rather easy to check that they form a ring. Another important ring is the ring of integers modulo n. In group theory, you've seen, in fact, maybe before group theory, you've seen that if I consider integers, the following relation on the set of integers. So if we say a1 and a2 are congruent mod n, precisely when n divides the difference between a1 and a2, then we've seen that this is an equivalence relation. We can consider the equivalence classes, and the equivalence classes of this equivalence relation are called residue classes. And the residue class of A mod n is nothing but an arithmetic progression. It is the arithmetic progression, it's the shift of nz by A. So if you think about it in terms of group theory, it's nothing but coset of the group nz in the group z. So in a sense, I can view the set of all the residue classes, I can identify it with the quotient group of z by nz. So it's an abelian group. With addition, it forms an abelian group, and we can define a multiplication on this set. And how do we define it? We take we take a representative from the first residue class, a representative from the second residue class, A and B. We multiply them, and we take the residue class of this new integer. And the point is that this definition, this multiplication is actually well defined. What does that mean? This means if I choose two different representatives of the same residue class, A1 and A2, and two representatives of the same residue class, B1 and B2, then their product are going to be equivalent to each other. So it is actually a well-defined multiplication, and then it's rather easy to check properties of rings. And one can see that the set of integers modulo n form a unital commutative ring. It is an important ring. We will be working with this ring in this course. We use it as a toy model, and at the same time, we use it in order to show irreducibility of binomials or integers or rational numbers later on. So you should feel comfortable working with a ring of integers modulo n. Another source of examples, I mean, as I've pointed out in algebra, a good part of it had been about zeros of binomials. And let's connect it with this language of ring theory. In fact, starting with any ring, one can consider, one can construct a new ring out of it by looking at binomials with coefficients inside this ring. So for every ring A, we can work with binomials with coefficients in the ring capital A. So what are they? We can think about them as formal summations using an indeterminate x. So we have x here as an indeterminate, and we look at formal summations, a constant term a sub 0 plus a1x and so on, and then we formally multiply them What do I mean by that? We formally multiply them. So it means, okay, so in order to actually define it, it is sometimes useful to think about polynomials as infinite series, but with an understanding that we are doing algebra and not analysis. And that means we are assuming that it's a finite summation. So we are assuming that from some point on, all the terms are zero. But it is convenient to write it like that. This way we don't need to keep track of this extra n. Now, when I want to add two polynomials, we essentially gather similar terms like what we did in you did in junior high, maybe. So we look at the coefficients of x to the I from both of these polynomials and add them. And similarly, when I want to multiply them, so the idea is that I'm going to have an associativity property, the distribution property and associativity property. So here actually we use the distribution property, and then we distribute the first summation to the second summation. So this means for every I, we get the ith term, a sub I x to the I, and multiply it by all the other terms of the second one. But now you see that this is a double sum. I don't want to have it as a double sum. I want to have a polynomial. This means I have to gather all the similar terms together. So by gathering all the similar terms, I have to understand under what conditions I'm getting the same term. So this means I plus j should be a fixed number. So let's say it's k. If it is k, then I can only vary from 0 to k. So this means I am gathering all the guys where the indices add up to k, and then I'm multiplying a sub I by b sub k minus I and adding them up. So this way I can in fact define the product of two polynomials this way. So this red part, the red part, you should view it as a kind of motivational background. And this is a definition that we are using. So this yellow one is the main definition of a product of two polynomials. Okay, so now we define product, we define addition, and one can check the properties of rings. I will not do it here. You can do it on your own. But for the purposes of this course, it's important that you believe that it's a ring and be able to do computation in different rings. If A is the ring of integers mod n, if A itself is ring of polynomials, and so on, you should be able to compute a product of polynomials and add them. Okay, so let's see one example to understand it a bit better. And in fact, we will do more in the discussion and problem session part of the course. So for that part, I ask you to work out what is 2x plus 1 times 2x squared plus 3x plus 1, but not in the ring of binomials the way that you have done it. You should think about the coefficients living inside the ring z mod 4. And do the same for x plus 1 to power 3 in the ring z sub 3 bracket x. So again, here we are working with the ring of integers mod n. In fact, let's do more and consider x plus 1 to power p. But here we are working with ring of integers mod p. And the assumption is that p is prime. So do these things, think about them, and be prepared for the discussion and problem session. Okay, so what is the hint? The hint is you should review the binomial expansion. And we will see and discuss it a bit more. So review the binomial expansion in order to be able to understand this part. Not the first example, but rather the last one. For the last one, review binomial expansion. Okay. Now, we've seen more examples of rings. Let's see how we can construct new rings out of old ones. Again, we had so far 2 examples of that type. We've seen how to use matrices in order to construct a new example out of an old example. We've seen how to use polynomials in order to construct a new example out of old ones. Another way is by looking at Cartesian product of rings. You've seen this kind of constructions for groups, but one can extend it to rings as well, essentially by component-wise multiplication. And by component-wise addition, we can consider the n-tuple of elements, ai belonging to the ith ring, and that way we can construct a new ring out of old ones. For instance, if I look at the ring of integers mod ring of integers mod 5 and look at its direct product by the ring of integers mod 6, then 2 times 2 comma 2 times 3 comma 3 in this ring is, okay, what is it? I have to multiply 2 by 3 in the first ring in z sub 5, and then I have to do the same thing in the second ring in z sub 6. In z sub 5 it is 1, but in z sub 6 it is 0. So you see, it's rather easy, but you have to keep track of, you have to understand that in the ith component, the computation of the ith component is done in the ith ring. So you have to borrow multiplication and addition inside that. Okay, so now let's see basic properties of addition and multiplication in an arbitrary ring. One of the basic properties is the following, that in any ring, when I multiply 0 by an element, I will end up getting 0. So let's see why this is the case. So we start with basic properties of 0. So 0 plus 0 is, of course, 0. Now I'm going to multiply both sides by a. And as I multiply a from, let's say, left, so I've done it here by right. Okay, so let's multiply a from right, and then I use the distribution law. So here I'm using the distribution law. So I get that it is 0 times a plus 0 times a, and that is the same as 0 times a. Now I can use cancellation because plus is, because a and plus is an abelian group. So I can actually add the negative of 0 times a if it's needed and cancel it out. So this way, because it's an abelian group, I'm allowed to cancel it out, and I end up getting that 0 times a is actually 0. We can do the same from left, and we get the first property of operations in rings. Now let's see more properties of operations in rings. For instance, in any ring, when I multiply negative a by b, I end up getting negative of a times b. Or when I multiply a by negative b, I end up getting, again, the same thing. But let's try to understand what it means. So this means that when I add it to a times b, I end up getting 0. So let's recall that when we say negative a times b, it means a times b plus negative a times b is 0. Or when we say negative a, it means a plus negative a is 0. So this, remember that when we say negative, it means this. It's inverse with the operation addition. Okay, so when we want to show the first equation, that negative a, when we want to show that negative a times b is the same as negative ab, that means we need to show that this guy plus a times b should be 0. I mean, this is what we are looking for. That's what we are seeking. So we have to add them and show that it is actually 0. We add them, and then we realize that when we add them, I can factor out b. Here again, I'm using the distribution law. So here we are using distribution law. Now the first property can help us. Notice the negative a plus a is 0. Now the first property helps us, and we get this by the first property that we showed. Similarly, I can do from the other side and get both of these claims, as you can see here. Now, the other property of operations in rings is the following: that negative a times negative b is the same as a times b. But what is it? It's two applications of the second property. So when I multiply negative a by negative b, think about this as one element. So it, and then plug it in over here. So you can call this guy, okay, I'm just putting it whatever it is over here. So the second property tells me that negative a times something is negative of a times that thing. So I put that thing over here. So I get that negative a times whatever it is negative of a times that thing. Now I use the same thing as the second equation as over here. I'm going to use this color now. So if I focus on this part of the equation, now I can put it over here. I see that a times negative b is negative of a times b. And negative of negative, here we are using again a fact from group theory, that negative of negative inverse of inverse is the element itself. And that's for the last equation. So that's how we know negative a times negative b is just a times b. And this is true for every ring. Okay, so far so good. Something that I claimed earlier was that in a unital ring, there is a unique element with the property that 1 times a is a times 1, and it is a, and I said that we call such an element the identity. Let's prove this and use it for the, later we will be using this. Okay, so let's see why this is the case. So suppose that I have two such things. Let's call them 1 and 1 prime. So both of them have this star property. So both of them have this property that when I multiply them by something else, I'm not going to change it. Okay, so now because, let me change this. So because 1 prime has the star property, so 1 prime has a star, satisfies a star, I do know that 1 times 1 prime is 1, because 1 prime multiplication by 1 prime does not change the element. So this, because of this, I get the first equation. Now, because 1 satisfies the star property, I know multiplication by 1 doesn't change my element. So because of this, I get the second equation, and that these two together imply that 1 is 1 prime. So there is only one element inside a unital ring that satisfies the star equation. Okay, so, and we call that element the identity of this ring, and sometimes we denote it by 1 sub the name of the ring. So that way we know that we are talking about the identity of this ring. Okay, so now whenever you learn a new structure in mathematics in general, in particular in algebra, you should ask yourself about the substructures and the maps that preserve that structure. Okay, and what do I mean by that? Let's recall that in linear algebra, when you learn about vector spaces, then you learn about subspaces, and you learn about linear transformations. So linear transformations were functions between vector spaces that preserve the vector space structure. And subspaces were subsets of a vector space that have the same properties, meaning with the same scalar multiplication, you could get elements within the same subset, and you could add or take the difference within that subset. Or in group theory, you learn about subgroups and group homomorphisms. We can do the same in rings, and we can talk about subrings and ring homomorphisms. So what is a subring? A subset of a ring with binary operations, plus and dot, is called a subring if with the same binary operations it forms a ring. So what are the examples? Okay, obvious examples are that the set of integers is a subring of rational numbers or real numbers or complex numbers. And the set of rational numbers is a subring of real numbers and complex numbers. And finally, real numbers is a subring of complex numbers. Now, for the discussion and problem session, please think about the following questions. What is the smallest subset or subring of complex numbers that contains both I, the imaginary number I, and Q? What is the smallest subring of complex numbers that contains both root 2 and Q? How can I describe the elements of such subring? How about if I add the third root of 2 to Q? What can I say about the elements of the smallest subring that contains this? We will be discussing this in the discussion and problem session of this course. Think about them before that section. Okay, so now, as I said, we want to understand, whenever we are given a new structure, we have to understand the maps that preserve that structure. Now, the maps that preserves structures of a ring, of rings, are called ring homomorphisms. So what is a ring homomorphism? When I give you two rings, A and B, then a function f from A to B is called a ring homomorphism if it preserves addition and it preserves multiplication. But there is a caveat. I mean, you have to be careful. When I say f of A1 plus A2, this is happening inside the ring A. When I say A1 times A2, this is happening inside the ring A. But when we say f of A1 plus f of A2, this one is happening inside the ring B. When I say f of A1 times f of A2, this is happening inside the ring B. One of the important examples is, of course, the residue map. So remember that by definition, so if I define C sub n of A from the ring of integers to the ring of integers modulo n to give me the residue class of A, then it's a ring homomorphism. Why? Because simply Cn of A plus B is what? Is, by definition, the residue class of A plus B. But how do we define the residue class of A plus residue class of B? It's exactly the same. This is precisely C sub n of A plus C sub n of B. Now, if I check the other property, so we need to understand what this guy is. This is precisely A times B, the residue class represented by the product of A and B. But on the other hand, if I consider the product of these residue classes, so what are they? It's the residue class of A times the residue class of B. By definition, it is the residue class represented by A times B. So we get that it is, in fact, a ring homomorphism. So in the next lecture, we will continue discussing more properties of ring homomorphisms, and we will discuss kernels, image of a ring homomorphism, We will see that they are subrings and so on. So till the next class.